So let's look at finding the length of a curve that's been defined parametrically. And this will be easy. We can kind of piggyback off of what we already developed from Cartesian. So here's a picture of a curve from some t equal a to some t equal b. And maybe I'll label the direction of motion. So increasing t there from a to b. That'll be important in a moment. So remember from previously, the idea was we approximate that curve with a bunch of line segments. And then as those line segments get shorter and shorter, they do a better and better job of approximating the curve, and eventually becomes the length as the norm of the partition goes to 0. And we found that delta s sub k by Pythagoras was the square root of delta x sub k squared plus delta y sub k squared. So right now, there's really nothing new about what I've written there. Now, when we did this in Cartesian, we wanted to end up with a Riemann sum involving delta x or delta y, and we achieved that by factoring out. But I'd like to have an integral of t, right? Because this curve is defined as a function of the parameter t, parametrically. So I want to introduce t into this. And so we can simply multiply by a form of 1. As we move from that point to that point, there is some change in t, right? There's a change in x and y that has to do with that, but that we can say that there was some change in t from there to there as well. OK, now this t I'm going to bring inside the square root. So the square root of the square, right? So as it comes into the square root, it's going to become delta x sub k over delta t sub k squared plus delta y sub k over delta t sub k squared. Now, this statement and this statement are only equivalent if the change in t is positive, right? Because what I have essentially said was that if you pull this back out, the square root of delta t squared is delta t. Well, the square root of a square, as I've mentioned a couple of times, is really the absolute value, not just t. But if we assume that we're going to go from a smaller time to a larger time, so in the direction of motion, then we're OK. And then I still have a delta t sub k outside. So this statement is equal to this one so long as we're talking about a change in time that is greater than or equal to 0, right? So that'll be key when we set up our limits, that we're always going in increasing time as we set this up. OK, well, and then you can see where this is headed as far as you take the norm of the partition to 0, these are going to become our derivatives. And we'll have that length is the integral from t equal a to t equal b of the square root of dx dt squared plus dy dt squared dt. So we have a new arc length differential now, right? We talked about how universally you could say that length is the integral from a to b of ds. And I said the details of ds will be embedded in there depending on the context. So now the arc length differential is this thing, a little bit different than the arc length differential we had for Cartesian. OK. So let's look at an example here. And for our example, x equals t cubed, y equals 3t squared over 2. And we're going to go from t equals 0 to root 3. So there's our curve. We need the length. And a little bit of detail. Obviously, these derivatives have to be defined over that whole thing, and they are here. And we need to be going in increasing time. So our length 0 to root 3. And square root dx dt is 3t squared. Dy dt, 2 comes down, cancels the 2. We have 3t squared dt. So just applying the formula we just derived. So what do we have? This will be now we have to put our integration techniques knowledge to work. We see a common factor in there, right? There's a 9 and a t squared, so that would come out and be a 3 and a t, right? Square root of 9 is 3, square root of t squared is t. Now, should be absolute value of t, right? The square root of t squared is absolute value of t, but we're going to be running from t equals 0 to t equal root 3, so t is not going to be negative. And then we have t squared plus 1. So we can ignore that absolute value, but now we have something that we can integrate by u substitution. If u is t squared plus 1, du is 2t dt. We're going to have the integral. Now I got to switch my limits. And t is 0, u is 1. T is root 3, u is 4. 1/2 du is t dt. So the t dt is a half du, so I pick up a half. And then square root of u du. That antiderivative is just u to the 3/2 from 1 to 4. 4 to the 3/2, remember this just means take the square root and cube it. So the square root of 4 is 2, cubed is 8. And square root of 1 is 1, cubed is 1. So 8 minus 1, or 7, for the length of our curve. So remember from the beginning of the semester when we looked at length, you're going to be using some techniques of integration here, right? Because square roots are, by their nature, troublesome. So hopefully you can factor something out so you can do a u sub, or remember, if you can't, then you're looking to make this a perfect square, either by a trig identity or something like that.